Okay, the presentation that you've got right here on shielding effectiveness will teach you how to build a shield, whether it's a shielded enclosure or a shield between a transmitter and a receiver. This presentation will allow you to have all of the stuff that you need to know as a ham to be able to create that shield. It uses shielding effectiveness calculators that are on the internet, and it's actually got links in there that you can just click on and it will take you to that site, and you can just plug in, I've got copper, it's this thick, and here's the frequency, and here's your 58 dB of shielding effectiveness. The presentation, the PowerPoint for this, I've already given it to Barry, and Barry's put it on the website under the members section, so you can go and download this thing and use it whenever you need it. So okay. So the first thing to go through here, I'm going to try to get through these fairly quickly, and so all this is out there, so you don't need to take any notes or anything. If there are any questions, give me a shout. Okay, an electromagnetic wave consists of a magnetic wave and electric wave. As it propagates, you get magnetic, electric, like you see in this little diagram. In order to build a shield, you've got to be able to shield the magnetic and the electric. So what's an electric field? Academic description of it, it's a property in space where a force is generated on a charged particle by charge. So if you've got a positive charge here and you bring another one up near it, just like it's diagrammed there, it'll experience a force that'll push it apart. This electric field shielding effectiveness. So imagine you've got like a beach ball, and it's non-conductive, and all around that sphere you've got positive and negative charges. You take a point charge and you bring it up next to that ball, that electric field will go right through that ball like it's not even there. And if you change that ball out for one that has more conductivity, some of the electrons are going to pull around to that side. It's going to be attracted by that positive charge like you see here. So the field on the inside is actually canceled out and begins to reduce. So if you have a sphere that's now conductive, highly conductive, then enough electrons are going to go around to that other side, and it's going to essentially cancel out all of the electric field going through the inside. And this is called a Faraday cage. Everybody's heard that probably one point or another. But Faraday cage is great, but it only shields from electric fields, not magnetic fields. So that adds a little bit of a twist to that. So everybody's seen a magnet, but what is a magnetic field in reality? And it says basically magnetic fields are produced by flowing electric currents that are either macro in scale, like current flowing through the wire around that little solenoid you see there, or it comes from the flowing currents that are in the magnetic material due to the electrons orbiting around the atoms. So that's what basically a magnetic field is. So, but now we have to get into the other side of it, where how do you shield from a magnetic field? Okay, one way of doing that, of the two different ways, is that you can create a sphere and you can use a magnetically permeable material so that the magnetic lines of force, I think I got this thing here if it actually works. Yeah, the magnetic lines of force, instead of just going straight through it, they have a path of least resistance to where it goes around, and then on the inside you end up with a very, very small amount of magnetic field. Okay, now the second way for magnetic shielding is pretty interesting, and this is one of the really good things that I didn't really have a real good grasp on. But if you take a magnetic field, let me back up a second. If you take a 1 foot thick wall of copper, and you take a magnet on one side and some sort of magnetic measurement on the other, and you wiggle that around, that even a 1 foot thick wall of copper, that magnetism is going to go right straight through it, just like it's not there. Now, if you put it on a axis and start spinning it so that that field starts alternating, at some point, that magnetic field that goes through there, it's being measured by the instrument on the other side, it will disappear entirely because that copper will stop the magnetic field coming through there because it's an alternating magnetic field, not a static magnetic field, just like you'd sit there and hold it with a magnet. In this particular case, you've got an alternating current going through a coil, and what happens is it creates these magnetic fields that induce these little blue circular currents in the material itself, and these are called eddy currents. And the effect that everybody's heard of is called the skin effect. So that's where with an alternating current, you end up with a little bit, you get all of your current basically being passed on the outside of the conductor. So get on through that. So the rule of thumb has been that with skin effect, you have a calculation of skin depth, and this is not something that you have to calculate, but unless you really want to get into it. But there's a formula here at the top that shows you how much your skin depth is on your conductor, depending on what type of material you've got and its shape and a number of things. But one skin depth will give you 8.7 dB of magnetic shielding in any kind of a conductor, but it doesn't necessarily have to be magnetically permeable. So that's why a Faraday cage that's made out of a conductive metal will shield you from an electric field as well as a magnetic field that has some frequency to it. And we're going to see here in a few minutes those frequencies. So to summarize this, there's only 3 points that affect the shielding based on the material you use, and that's the conductivity, whatever magnetic permeability it may have, and then the actual thickness of the metal. So in most cases, most shields, I don't know maybe if I'm saying that right, but a lot of shields are not magnetically permeable at all because they work just basically on the frequency that they're having to shield with. Okay, so there are now external factors that also impact shielding effectiveness that are outside of the design of the shield itself, and that's of course the incoming frequency, and then where is the location of that shield in relation to the source of the radio frequency. So I'm going to blow through this very quickly, but in an antenna situation, you have a near field and a far field. This side over here on this graph would be where your antenna is, and on one side you're seeing wave impedance, and then out here is a ratio of the wavelengths. So what happens is that the electric field impedance and the magnetic field impedance vary as you move away from the antenna. The bottom line for us is that at 0.7 wavelength, everything comes together, everything gets constant, and your electromagnetic wave moves through space at an impedance of 377 ohms. God said it, I didn't. You know. So the key here is that 0.7 wavelength, you're in the far field calculations, which are much simpler than the near field. So all of our work, since it's in the far field, that simplifies things. So for example, at 2 meters times 0.7, if you get 4.6 feet away from a 2-meter antenna, you're essentially working in the far field. Okay, so that's kind of a key point. So to back up and simplify this, we're always working in EMP. Since the thing's outside of our atmosphere, you're always in the far field. And here's the link to the calculator that we're actually going to use here in a second. Okay, so very quickly, let's look at what actually happens with a shield. You have an incident wave where this is coming directly in from your source. as we said earlier, in a plane wave, you're working with an impedance of 377 ohms. When that hits a shield, that shield impedance is very, very low. So what happens when you get a mismatch of impedances? You get a reflection. So when you're designing a transceiver, transmission line antenna, we always design to have all those impedances match as perfectly as we can so that we get as much power delivered to your antenna. When you're making a shield, you want to make sure that you got the worst possible impedance mismatch in the world so that you'll actually get a reflected wave. So there's some that gets reflected and there's some that actually is absorbed into the field and transmits to the other side, and whatever doesn't get absorbed comes on out inside your shield. The second boundary is another impedance mismatch, so you also begin to get reflections and these bounce around, but from a numerical standpoint, they really don't amount to much. So the power coming in is either reflected, absorbed, or transmitted through, and the shielding effectiveness computation is measured in decibels, and it's the sum of the absorption losses plus the reflection losses. Okay, now let's take a chance to build a shield, and we're going to build it out of copper foil. Okay, and it's only going to be 1/1000th of an inch thick. Okay, each one of these is 3 different runs on the internet computation. And in this particular case, we've selected a copper shield in all 3 cases. And when you click on copper, it puts in the conductivity and permeability in all cases. So then we have to say, well, how thick is it? We put in 1 mil to be foil in all 3 cases. And then in the frequency, we put in 100 kilohertz as one run, and 10 megahertz as another run, and 1,000 megahertz as the other. So nice thing about this, you push the calculate button, and in this first case at 100 kilohertz, that 1 mil of copper foil will create 118 dB of reflection losses, and since it's so skinny at that low frequency, it only gives you 1 dB of absorption loss. So the total shielding effectiveness that you get out of that is 119 dB. At a couple orders of magnitude up, same thickness, the reflection loss drops down to 98 dB, but the absorption loss raises to 11, so you're doing about 109. At a gigahertz, you're now working at 78 for reflection, 106 at absorption, and shielding effectiveness is 184. So the higher frequencies are much easier to shield against versus the low, but there's an interaction in that formula that kind of gives you a dip in the middle, and it goes up as you get into the higher frequencies. Now, I dug around the net and I found an actual plot for 1 mil copper, and what you can see here is you start down here at 0.1 kilohertz. The absorption loss is strictly a resistive loss, and as you start cranking up the frequency, it shoots to the moon as you get up in here into microwave frequencies. Now the reflection loss that you see here, again, far field, plane wave, this is what you're going to be working with once you get away from that 0.7 lambda, 0.7 wavelength zone. So at any frequency here, you know, at 1, we've got roughly 130 dB of shielding related to reflection and pretty much 0 associated with absorption. If you happen to be an equipment designer and you're working very, very closely, then you can see your magnetic field and your electric field impedance variance over here as well, or the impedance variance is causing the changes of electric field shielding effectiveness. So that's kind of an interesting thing, and it agreed with the computation that was on the network. So one of the big keys then when you're trying to build a practical enclosure is that you've got to have some way to close the thing up. Okay? And one way is to stick the lid on the can. Okay? So the real question, though, is from a numerical standpoint, how much shielding do you really get? Because that's not a perfect metallic closure. It's got some resistance, it's got some air gaps. So there's another shielding effectiveness calculator that Laird Technologies has out there. And what I did is set up a model where it would create a 5/100th of an inch gap, about like if you had a pot, you put a closer on it, that metal's sitting down there, the tolerances are, you know, it's not a perfect seal. It's not an airtight seal. So we're only going to run this computation with 5/100ths of an inch gap, and the way this thing works, you have to put some squares together and then pack them together to essentially simulate that particular configuration. What we came back with was kind of shocking to me because I didn't realize that this would happen. Down here at low frequencies, even that small gap doesn't mean a thing. It's up here right about in 120 dB. At about 10 megahertz, we saw a drop of about 6 dB over the at this frequency range. However, when you start running that frequency up 100 megahertz, 1000 megahertz, that little tiny bit of crack causes a loss of 161 dB of shielding effectiveness. I was really shocked when I first ran these numbers, and I went back and ran them several times and did some checking with some other folks. And these numbers are awful when you've got a gap. So a tiny crack of 5/100ths of an inch has essentially defeated the high frequency range of our copper foil shield. Now, let's design a real EMP shield. This particular diagram came out of MIL Standard 188, and this is what 12 years ago the military declassified as their design requirement for anybody selling EMP hardware into the military. And on this side you've got shielding effectiveness. Down here you've got the frequency spectrum. This is kind of really telling to see just how far the EMP pulse comes in terms of low frequencies. This right here is 10 to the third or 1,000 hertz. You're talking audio frequency is that low. But it's saying, you know, at 10 to the fourth you need about 20 dB of shielding according to what this minimum standard is. Once you get up into the AM radio zone, you're talking about 55 roughly. And then once you get up into the FM 10 to the 7th, or let's see, what is that, 10 megahertz through 1,000 megahertz, they're saying that the absolute minimum shielding effectiveness that you require to protect your equipment from an EMP pulse is 80 dB. And then after a gigahertz, it drops very quickly down to 1.5 gigahertz or 1,500 megahertz. And that's essentially saying that from their research that the frequency operation of a microwave oven, for example, at 2.54 gigahertz, there's no EMP radiation there. So here's another thought. I've heard a number of people talk about microwave ovens being Faraday cages. Well, is a microwave oven a Faraday cage?
Only for a specific frequency.
Yeah, yes and no is the answer here, because here's a cheapy FM radio inside of a microwave, and you notice the little "I'm playing music" button. I've got a good signal. So this thing, this cage that's built there is a Faraday cage, and it does keep the 2.5 gigahertz inside cooking your meals and not you, but your local radio station's helping at the microvolt level. But this little test basically just shows that if the radio plays inside, it's no good for a EMP shield. Okay.
You know what I find amazing about that is that the screen is small enough to shield out the microwaves, which are 2.4 gigahertz. But the FM frequency has a bigger wave, technically it should filter out the bigger wave.
You have to run the numbers, and it doesn't.
No, you know, because the wavelength is so much larger, you'd think it would have to 8 gigahertz would make it through, but the FM stuff would.
Yeah. Well, and certainly AM radio plays in there well because it's only 1 megahertz. So, you have a question?
Yeah, so if this thing blows up 300 miles up and the rays come down, they come down at whatever angle, straight, no deflection, no deviation, no ricochet. I mean, they don't do any harm to something with the proper, you know. So, I mean, like if you got everything covered under a dome, you don't have to worry about underneath?
Not necessarily.
Well,
No. Well, let me say this. The safe answer is no. Yeah, in fact, I've got a book that some PhD wrote, and he had a tinfoil cover over his entire car. Aluminum foil. Seriously. So, but at any rate, I want to show you a little quickie video here in a second, but there's a key point here. Right now, our military, or no other military on the face of the earth, is going to give out their information of how good their bomb is. Okay? Back in World War II, when the bomb was first used, the Starfish Prime bomb put off 50,000 volts per meter. So if you had a 1 meter piece of wire, 50,000 volts, 1 meter, essentially you'd measure 50,000 volts at that end. Or if you had a 6-foot USB cable, okay, that's about 2 meters. So that'll deliver 100,000 volts into your motherboard, okay? But the interesting piece about that is that those measurements were made near the equator. Over the United States, the magnetic field is almost double here as to what it is in the equator, because at the pole, the magnetic field goes up and then it spreads out to the fattest part and then it comes back together. So by having a higher magnetic field where we're at, if you take the same bomb and drop it up here, it's going to have twice the electric field. So the numbers that they were giving us well, let me play this little video here. Hello.
When we get a E1 transient, these transient fields can be 50 kV per meter, maybe even up to 250 kV per meter. So they have the potential to be able to impose a transient on that signal wire that can very much exceed the relay equipment normal operating voltage as well as any transient voltage.
This is the guy who gave this speech, and a great big long speech before the FBI InfraGard last month. And I had a chance to sit through the whole thing. And basically what he's saying here is that, and he's taking, from a professional standpoint, a lot of this stuff doesn't get spoken. He actually says that 250 kilovolts per meter is possible. You know, you're talking 500,000 volts out of that little USB cable. So that's pretty scary. But if you sit down and think about it, they were doing 50 years ago. Now they're doing 250. We've only had a 5 times improvement in 50 years. I don't believe it.
Many people don't actually realize. In arc, that's several thousand volts just from you dragging your feet across the market.
So if we're going to design an EMP field, EMP shield, what we want to do is come up with a number that we can feel comfortable with, that if it happens, we've got enough shielding in place. So the argument there about a 5-fold increase, I think, is something that it's disinformation that they're sending out, hoping somebody else is going to believe it, particularly an enemy. So my argument is, let's use 200 times that, and say 200 times is going to give us 10 million volts per meter as a threat level that we want to protect against. I think that's a pretty good shot. So if we go on the internet and pick up a voltage ratio calculator, we put in 10 million volts And what we want to do is drop that shielding, raise the shielding effectiveness up to where we drop 10 million volts of intensity to a safe 1 volt per meter actually inside of our shield. Okay, so what that says is that I need to have 140 dB of shielding effectiveness to be able to protect my electronics from an EMP pulse based on just a wild guess. So the question is, can we afford that good of a shield? Okay, so let's go back to our calculation where we were developing shielding effectiveness, and this time we'll use a 50 mil copper plate rather than just a plain old foil. Okay, so now we're using real thin copper metal, and we're going to run the frequency at 10 kilohertz, 100 kilohertz, 1 megahertz, 10, 100, and 1,000 megahertz. So now we find that we've got 145 dB of shielding effectiveness at your lowest frequency, and then very nicely, all your other shielding effectiveness raise up as you go up higher in frequency. So even though we've pulled a wild number out of the hat, that we want to make that 200 times, we found out now that the foil, it doesn't make much of a shield to begin with, and it's mechanically hard to deal with, and it's easy to damage. Now we can go with our high wild number and the critical frequencies that don't break the bank, and it actually works. Okay, but we still have two problems. That little thin copper isn't very strong. It's easy to, you can sit on it and mash it. Okay, and the other problem is that if you got a little crack in it, you put it together and it's not solid, then you've also got a little crack in there, and you're going to lose your shielding effectiveness because you don't have a good solid seal. So the idea, let's go back and run this calculation with a cheaper metal, but something that's going to be structurally rugged. So let's pick aluminum and raise the thickness to 1/4 of an inch of a wall. So the question is, can a thicker aluminum situation work as well as thinner copper? What we're finding out, if we go to 1/4 of an inch of aluminum, then for the same frequencies, we find out that our reflection losses and absorption losses shoot through the roof. We've got 193 dB of shielding at 10 kilohertz. You've got 320 at 100 kilohertz. As you start moving up in frequency, you get into some fantastic shielding effectiveness with 1/4 of an inch aluminum. And aluminum's pretty cheap. So, I've never even seen numbers, 21,000 dB. What the hell is that? Okay, but now that raises an interesting question. Where can you find an aluminum container that's 1/4 of an inch thick with thick walls and it's solid and airtight? It was funny. I actually pulled into my garage one day and I was thinking about this, and I thought, well, how are we going to make this? And I looked up on the shelf as I was driving in. I saw the wife's pressure canner sitting there, and I'm going like, damn, we got it. So you can actually buy these things off of eBay for anywhere from as low as $100 to several $100. But yeah, that's part of Sam's thing there. But has everybody ever not seen one of these? So this is an All-American, yeah. There's something particularly satisfying about having All-American stamped on something that's going to protect you from this.
Well, now, there's also the layering, too. So if you put a foil object inside of your can, you've got some shielding by the can, and then you've got another shield inside of that. So
and that's a point I wasn't going to talk about tonight, but actually that's a really important thing, because the radiation that does penetrate once it gets inside, it'll resonate inside there. So if you have something else wrapped up inside, you've got some additional shielding. But if you're talking about resonating at a frequency maybe 25 megahertz or something like that in a big tank, and you've got 800 dB of shielding effectiveness, you're safe already. So
You can't fit my Yates 950 inside that.
right. But to get a few things started, to put your couple HTs and stuff like that, I mean, you only use this thing one day out of 365. So you probably have it already, or if not, you know, you can pick one off of eBay, and it's a quick solution that you know is going to work.
Yeah, you talk about the frequency. Do we actually know what frequency one of those is going to be, or are we just guessing with these three versions of frequency?
The data is going to be classified from the government. The only thing I can really go on is the fact that mask that was introduced about 12 years ago, and they're saying that on the upper end there it dies off pretty quickly. But Sam and I were having this discussion on the way over. What do you really know? And from my perspective, we really don't, because the government's got all that classified, and whatever developments they've made with supercomputers and this, that, and the other over the last 10, 15 years, we don't know about that either. So all you can do is throw more metal at it to feel like you've got some level of protection. So
When you go to the air show, look inside their communications vehicles, see what they're doing. And you can see what shielding they're using on their radios. You'll notice that all their coaxes and coils.
So one of the things about it is that if you decided you wanted to protect your rig, or you wanted to take another rig and buy one and put it away, you could design your own cage with the formulas at those websites that are linked in this presentation. So if you want to build a box this big, get you some steel and put in the numbers for steel, weld it up, and you're good to go. Depends on, well, just put your numbers in there, and if it says 300 dB of shielding effectiveness, you're probably all right.
Bruce, there's no need to actually ground that. There's no need to actually ground the container first.
That's a question that comes up a lot, and there's a lot of discussion about that. And the only time you'd have to ground is when you actually have some sort of potential coming down that would go against the earth. When you're talking about these kind of frequencies, essentially they're coming in as a plane wave, and there's no potential difference against the earth, so you don't need to ground them for that.
There's also skin effect. Skin effect of the exposure.
Yeah, you know, again, the questions you guys are coming up with now are at the edge of my knowledge. So we'd have to go do some more digging, but it's been a really good chance to sit down and do some of these. I think Sam's got some equipment here that he wants to give a little bit of a shot to. And
Who's going to climb in the trash can?
Is any good?
Well, the only question, the purpose of the trash can was simply to maybe test some myths. I've noticed that the trash can, because it's metal, you just throw all your stuff in a trash can and you're protected. So we have a little demo that will show you if that's really true or not. And it would only take a minute to do that if you'd like to see it.
you can turn the lights on.
If you accept it,
Oh, we need this?
This battery compartment. Thank you.
Okay, the first premise was that a garbage can would effectively protect your gear. So what we have is a garbage can. Now, this is is an ultrasonic transducer, but it produces, it runs it right at 38.4 kilohertz. So if we put it inside the can and put the lid on it, and we can read ultrasonic outside of it, that means that whether it was radio or ultrasonic, that there is an escape from this can. If something will escape from the can, then it can also get in the can. So we would just put the transducer in here. We'll turn it on, so it's now generating 38.4 kilohertz. Well, it could resonate the can, but it just so happens it doesn't, because all of the transducers are acoustically isolated, so they're isolated from the case. But it is a good point. So, all right, so we'll turn this on, and
You get all these expensive toys.
well, we design and build these. So I don't know if you can see this, but I'll just take one of the transducers, and some of them we have turned off on here. Yeah, we did have. There we go. So this one is working. I don't know if you can see the display. You can see this little bar graph display jump around over here. Can everybody see that? Okay. So that, huh? Yeah, if you want to move up. Anyway, there's a bar graph display on here, and it basically went to the rail when I subjected it to the ultrasonic. So we're going to drop this in the can, and we'll put our lid on it. Okay, so does everyone accept that if something can get out of it, it can probably get in the same way it went in? So, all right, so I'm reading zip right at the moment, and I'm going to put my sensor over close to the can, and what do we see? So, does everybody see that? I'm sorry, I can't hear you. Okay, now, to your point, if I take it and just put it down instead of what I'm getting, it's very small, but it's leaking down here. I've changed the angle of it. It is not resonating the can. I'm actually measuring the leakage. Okay. Okay, so that's just one demo that at 38.4 kilohertz, and you see how long that wavelength is. Well, if you shorten that wavelength as those frequencies get up, this looks like just a train station ride through it. It basically, this offers zero shielding to whatever it is that you're trying to protect. And then the other, I'm sorry, was it a question?
Check the seam where the...
Yeah, check the seam, just get higher output.
No, let's see the seam where it's put together. See if
Yeah.
it's leaking through that seam. That does good.
Well, if I turn it right down here, it is possible. It is possible. But my suspicion is that what I'm getting right through here. Now, it might be different if we welded this whole thing up. That would make a difference, but the odds are you can't get your stuff in and out very easily. So this is at 38.4.
Stick your HC in there.
Yes. No. It's ultrasonic. That's kilohertz. Okay, and then Has anybody got their cell phone? Oh, let me turn my, I turned the sound down on it. Now, does now it's possible? Do we get cell phone coverage inside of the building here? Because when I did this at the house.
Somebody else has got an HT in here.
It's kicked off the voicemail. Okay. Well, when I did this at the house, it just rang. It had no problems at all.
Pull it out and see if I can hold it.
Oh.
Here, we got a tight fit.
Unfortunately, if it rings, it proves that it's no good. But if it doesn't ring, it doesn't necessarily prove that it is good for EMP. That's the key.
That's why I'm saying throw some more power at it. Get a 100-watt transmitter. That's what we put
All right. Let's just try one more time. Well, that's whoops. There's more phone signal over here by the window.
Hey, we're still here.
Okay.
Turn it upside down.
Huh? Oh, okay. So a lot of it's coming through the crack in the Now we need something to get it off the. Yeah, that's good. That's good. All right. Okay.
Hey, Sam, give me your cell phone number again.
542-6191. I don't hear anything. So this is one that Bob made.
Bob made that?
Well, it's airtight and but he put a copper seal around it. That's not your everyday ammo box, right?
That's not a regular ammo canister.
Huh?
That's not a regular ammo canister.
No, he put well, it's an ammo can, but he's got a copper braid around the seal area so that you've got metal to metal contact. No, he's got a solid copper braid all the way around so that it's metal contacts the copper. Now we could put the cell phone inside your aluminum, but I think we're good.
I think probably good there.
Yeah. Okay, so the